Okay, so a 1,500 kilogram car travels at 12 meters per second. The driver sees a dog crossing the road, applies the brakes to avoid hitting the dog, and manages to stop the car in 50 meters. Part A. Find the force of friction used to stop the car. Now, in order to solve this, you could either use Newton's second law, or you can use the work-energy theorems. Today I'm going to show you how to solve this question using the work-energy theorems, as well as the work equation. So to begin, let's start off by drawing a diagram of what this scenario looks like. So we have a car, like this, and it's moving. And then at the end here, it comes to a stop. Now I drew it in red to symbolize that it is at a stop at this point. And it's on a straight road. So the next step is I like to draw my free body diagram so that I can see all the forces acting in this system. So the first one we have the force of gravity, which is mg, and we also have a normal force acting up on this. We also have the force of friction, right here. And this isn't static friction, this is kinetic friction. If it were static friction, this thing, then you'd have to decide whether it's moving or not. But because it's moving and the brakes are being applied, it's still going forward, it's using kinetic friction. The next thing is, let's look at the question a little bit more carefully. So we have a mass right here. That's important to know because when we use kinetic energy, we know the formula has a mass value in it. And we have the initial velocity right there. We also have a distance or a displacement, and that'll come in handy for when we use our work-energy theorem, when we use the work equation. As you can see, we can plug in the value here. And we also have our final velocity because it comes to a complete stop. When it's at a complete stop, it's going 0 meters per second. So this is 0 meters per second. So now we have some initial things to keep in mind. The next step is to identify which forces are conservative and which forces are non-conservative. So I'll write it here. C stands for conservative force, NC stands for non-conservative force. The only conservative force in this system is the force of gravity. As for the non-conservative forces, there are two. We have the normal force, and we have the force of friction. The next thing we need to ask ourselves, do the non-conservative forces do any work on the system? Let's look at the normal force. Does the normal force do any work? And the way you can evaluate this, in your mind, we know that the work equation is a force times a displacement times the cosine of an angle between the force and the displacement vectors. So The normal force, which I'll draw in red, is pointing up. And the displacement vector, which I'll draw in black, is pointing towards the right. Because if you imagine this system right here, look up here for a moment, the car is going to the right or maybe the left, however you draw it. And it's going this way. But the normal force is always acting upwards. And because you have a 90-degree angle, when you go to solve the rest of this question, we don't need to know what the force is. The displacement is 50. But the cosine is the cosine of 90. And the cosine of 90 is 0. So this does no work. Let's apply the same reasoning. Let's apply the same evaluation for the work done by friction now. So the work done by friction. So we have a force. We don't need to know what the force is. We have a displacement of 50. But what about the angle? What is the angle? So remember, the angle has to be between the force, in this case friction, and the displacement vector. So I'll draw the force of friction in red, and it's going to the left. So this is friction. And in black, I'll draw the displacement vector. This is our displacement vector. Now, if you draw the angle, it forms 180 degrees. So the angle is 180 degrees. And if we solve for this, we get a negative 50 times our force of friction. And what this essentially tells us is, yes, the force of friction is a non-conservative force that does work on the system. Therefore, this makes the question a little bit harder because now we have to use either the work equation, the work energy theorems, or a combination of the two. Now that we have that taken care of, we know the friction does work. So we can apply our work energy theorems. Now the first one is the net work, and that is delta KE. We also have the work done by non-conservative forces, which is delta E. And keep in mind that delta E in this system, it changes for every system, but in this system, we're dealing with the change in gravitational potential energy plus the change in kinetic energy. Lastly, we have the work done by conservative forces, which is a negative delta PE. For this question, let's use the second work energy theorem I have listed. Now I'm going to get rid of these. And let's begin using the work energy theorem. So we said work done by the non-conservative forces will be equal to the work done by friction because it's a non-conservative force, which is equal to delta PE plus delta KE. Now let's analyze this free body diagram yet again. We said we know that potential energy is equal to mgh. Now in this system, the height does not change at all. Potential energy in the beginning is going to equal the potential energy in the final. Because the height is 0, our initial potential energy will be 0, and our final potential energy will also be 0. Therefore, we can claim that this will be 0. We can cancel this part of the expression out. Now, if we continue writing, we know the work done by friction is therefore equal to the change in kinetic energy. And if we continue to write this out even further, we know the work done by friction is 1/2 mv final squared minus 1/2 mv initial squared. Now again, let's take a look at this question. We said that the final velocity is 0 meters per second, and that's because it comes to a complete stop. Therefore, we can say this equals 0. So we can cancel this part of the expression. So if we continue to further write out this equation, we can say that the work of friction is negative 1/2 mv initial squared. And if we go ahead and solve this, we have the work done by friction is equal to negative 1/2 times 1,500 kilograms times 12 meters per second squared. And if we decide to fully solve this, the work done by friction is equal to negative 108,000 joules. So we're done, right? Not necessarily. That only gives us the work done by friction. The question is asking to find the force of friction. So you might be stumped here, but what you can also use is the work equation. If you recall this, and we can also apply it for friction. So the work done by friction let's go ahead and solve this now. So the work done by friction is equal to, do we know the force of friction? No, we do not. And it's not necessary yet. We can just leave it as this variable. Do we know the displacement? 50 meters. And the angle, if you recall, is 180 degrees. So if we continue to write this out, the work done by friction is the force of friction times a negative 50. What we can do here now is use substitution and solve for the force of friction. So I'm going to write that again over here. So we said the work done by friction is equal to a negative 50 times the force of friction, and the work done by friction is also equal to negative 108,000 joules. Now, using substitution, we take this expression and substitute it right there. And now we can set them equal to each other. And solve for the force of friction. So ultimately, the force of friction will be equal to 2,160 newtons. And that's how you solve part A, using the work equation combined with the work energy theorem.